Hello, we're still in lesson number 3. Here's a term I want to tell you about. It's called the hole system. When we're doing fits between shafts and holes, the hole system is set up where the basic size of the hole, the nominal or the smallest hole, is the nominal size. So in this case, the nominal size is a 1/2 inch, so therefore when we apply the tolerance, then it's still a 1/2 inch is the basic hole size or the smallest hole. It's the fits are all based on changing the shaft here to fit this hole system. There would be another, and this will make more sense when we talk about this with standard fits, but the shaft system is kind of like the opposite. So the largest shaft is the nominal size. So the tolerance of the shaft is such that the largest shaft is the nominal size. That's called the shaft system. Now I'll tell you right now is we're going to be using the hole system because we have tables, ANSI B4.2 tables that we're going to use for these calculations. It's part of your homework. It's actually the second problem in your homework is calculating the limits based on the specified fits. And we'll talk more about that in a minute. Now, we're going to be creating drawings in this course, and these drawings have to go out and they have to be correct. So therefore, all features have to have tolerances specified on the drawing. You can do this several different ways. If you had the same tolerance for every feature on the drawing, which really isn't that realistic, but if you were, all tolerances plus or minus 1 millimeter unless otherwise noted. Angles 1 degree. This could be a general tolerancing note. If you had a note like this, it tells me that everywhere on the drawing, regardless of whatever the feature is, here's the tolerance plus or minus 2 millimeters. That is a general tolerancing note. Limit tolerances. Limit tolerances state the upper and lower limits of a dimension range in place of the dimension. Okay, so what we're saying here is this is a shaft here, and the diameter of the shaft can be a maximum of 19.02 millimeters, or it can be a minimum of 18.79. So instead of specifying a nominal and a tolerance, we're specifying the tolerance by using limit dimensions placed on the drawing. And when we do limit dimensions this way, we could either do it in a single line form like this, or we can do them stacked. Okay, when you do them stacked like this, the largest number is always above the smaller number. The upper value is always placed above the lower value. Okay, so that's a limit dimension. Single limit dimensions. These could be like a min or a max. So in this case, let's see. I have to blow this up here. It's a maximum dimension. So it's a dimension that's specified as a maximum or a minimum only. That is a single limit dimension. Okay, plus or minus tolerances. There's a unilateral plus or minus tolerance. Okay, in this case, we have a nominal and a unilateral plus or minus tolerance. In this case, it's 1.878 plus nothing minus 2 thousandths. So if you're talking about inches, the decimal place 002, that stands for 2 thousandths is the nomenclature we use. It really stands for 2 thousandths of an inch. So the unilateral dimension says all the tolerances are specified on one side of the nominal. Where if you had a bilateral, you have tolerances on both sides of the nominal. That is a plus or minus tolerance versus a single limit dimension, that's a min or max dimension, versus a limit tolerance, which is given as just the limits, the size limits of the part, not a bilateral tolerance, which has a nominal and a plus or minus, or a unilateral, which has a nominal and a plus or a minus. Okay, angular tolerances. Angular tolerances are usually bilateral and given in terms of degrees, minutes, and seconds, unless you're using GD&T. Okay, and here's some examples of angular tolerances. Here we have a bilateral tolerance. Here we have limit tolerances. Here we have bilateral tolerance, and here we have a unilateral tolerance, 0.045 max. Tolerance stack up. Here's a term, chain dimension. Uses one end of a dimension as the start of the next. Okay, so in baseline dimensioning, what we have here is we have this line, we'll call this the baseline of our object, and we're taking the location of these steps off of that baseline. So that's called baseline dimensioning. Now, if you use chain dimensioning, that's another way to do it. It uses the end of one dimension as the beginning of the next. Okay, you can have tolerance stacking here because of these chain dimensions, and in some cases it's better to do baseline dimensions. I can't really say which one's the best because really all tolerances need to be calculated based on the fit of and function of the part. But yeah, these are two common ways of doing things. You have a chain dimension here, or you have a baseline dimension set up here. This gets into the using the national standard limits and fits tables. This is the second problem in your assignment 3. And what it is they have a list, this ANSI B4.1. It's a preferred limit for cylindrical and fits for cylindrical parts, defining the terms and recommending the preferred standard sizes, allowances, tolerances, and fits in terms of the decimal inch. Okay, it's only in inches. This standard gives a series of standard fits, classes of fits, on a unilateral whole basis. So I provided the charts. They're in your material folder for the ANSI B4.1. They're in your charts. And then there's an example problem, for lesson 3. You want to review that example problem. I'll put a movie in there too to walk through the example problem, but that'll tell you how to use these tables. So essentially what happens here is there's these classes of fits that are defined, and by using the tables you can determine the class of fits, and we'll talk about that a little bit more when I can show you the tables. So tolerances and machining processes. It's true that different machining processes have different capabilities in terms of what tolerances can be held. And this chart here shows that, well, when we're up and around in higher tolerances here, that's our milling and drilling. But if we want to get tighter tolerances in here, like to the tenths of thousandths, like 4 decimal places, we've got to be using lapping and honing and grinding and diamond turning and boring. So this chart here kind of gives you a picture of how manufacturing processes generate the tolerances on your parts. GD&T. We're going to talk a little bit about GD&T. There'll be another movie for this. And essentially, really, it's all what we're going to do with GD&T is we're going to talk about these different symbols and how to apply them. GD&T is a whole another course. So what we're going to be talking about here is just pretty much how the basics of how to use GD&T and what some of the symbols mean. It's really hard in a course like this to get into all of the GD&T and explain to you all the meanings, because it is a rather unique way of looking at things. It is a great way of defining parts. So what I'm going to do here is I'm going to end this lesson right here. There'll be another one on GD&T.